In languages like Java or C++, objects are forged from rigid, immutable blueprints. But JavaScript operates on a different architecture. Under the hood, it is a dynamic, live-wired network of floating nodes, constantly severing and reattaching their connections in real time. We can see this architecture at work in a simple code snippet. We declare an entirely empty object literal. We then call the dot-to-string method on that empty object. Instead of throwing an error, it executes successfully and returns object, object. In classical object-oriented programming, an empty container should possess zero behaviors. It has no methods, no properties, and no internal logic defined by the developer. Yet the engine clearly finds a method to execute. When developers cannot trace this hidden execution path, they often struggle to debug performance bottlenecks or unexpected side effects that occur when inheritance trees become complex in production. Modern JavaScript provides the ES6 class keyword, making the language appear similar to its classical peers. However, this syntax is an intentional abstraction designed to mask the actual runtime mechanics. This abstraction dates back to 1995. As Netscape prepared to launch JavaScript, Java was the undisputed standard for enterprise computing. To attract those developers, management mandated that this new, flexible scripting language had to mimic Java's appearance. This corporate mandate led to the creation of constructor functions. They were designed to look like classical blueprints, but they function as an entirely different mechanism beneath the surface. To understand the system, we must map the property lookup algorithm step by step, resolve a naming collision in the language's core, and master the mechanics of direct object delegation. Exposing these engine mechanics allows us to predict how our code interacts with memory, rather than relying on behaviors we expect from other languages. At its core, a JavaScript object is an unordered bag of properties. It maps string names to specific values or functions. Look at property bag A. We attempt to read property B. The engine checks local memory, but it's missing. Instead of throwing an error, it traverses a hidden upward linkage to a parent object, finds the matching property, and routes the data back down. The inverse rule applies when writing data. If you assign a value to a.b, the engine never traverses the upward linkage. Assignment operations strictly create or update an own property in the local memory space of the target object. JavaScript does not inherit behavior by copying methods from a blueprint. Instead, it shares behavior through these live, delegated memory lookups. Because assignments are local, we encounter a mechanism called shadowing. Writing a property locally that shares a name with a property on the parent intercepts the search pulse. The parent property remains intact, but it is effectively hidden from the local object. This shows the architectural payoff. On the left, 10,000 objects each receive a complete, duplicated copy of all methods. On the right, 10,000 lightweight nodes are wired to a single central logic block. Prototypal delegation serves as a memory optimization strategy. It allows thousands of distinct objects to share a single copy of a function in memory. Utilizing this linkage requires navigating a naming collision between an internal engine mechanism and a public property. On the left is an object instance. Its glowing upward cable is the active internal linkage, called double bracket prototype. On the right, a constructor function has a standard .prototype property. This isn't an active cable. It's a payload box of methods for future objects. If you take a standard instance object and try to read its .prototype property, it will evaluate to undefined. That property only exists on functions. Conflating the active internal cable with the function's static payload property is the source of many prototype chain bugs. We see how these concepts interact by breaking down the new keyword. Using it before a function call triggers a strict automated sequence. First, the engine allocates memory and creates a completely blank object. Step 2 is the wiring phase. It extracts the constructor's .prototype payload and welds it to the new object's internal double bracket prototype port. Finally, the engine binds this context to the new object, executes the logic inside the constructor function, and returns the finished object. The new keyword automates the wiring of the internal prototype cable, functioning as a syntactic shortcut for these manual memory operations. Object.create operates directly on these linkages, establishing the prototype chain without the abstraction of constructor functions. Object.create takes an existing object, generates a new empty object, and links its internal cable to the existing one in a single step. Pass null into it, and the engine explicitly caps the upward linkage.
the new object floats completely isolated. Because it has no prototype cable, a null prototype object cannot delegate lookups. It lacks default methods like the toString method we saw earlier, which prevents it from being affected by prototype pollution. Utilizing object.create allows developers to define inheritance structures through direct object relationships rather than function wrappers. Pulling back from individual components, these individual linkages form the macro structure of the entire JavaScript runtime. This tree maps the system. Thousands of instances, arrays, and functions trace upward, delegating behavior to mid-tier nodes like array.prototype and function.prototype. Every path ultimately funnels upward, converging at a single apex, object.prototype. This node houses the base methods the entire ecosystem relies on. Above object.prototype, the internal linkage finally points to null. The search pulse terminates. The chain is complete. Navigating this data tree allows for precise management of memory and property lookups across the entire application lifecycle. Understanding how these nodes connect determines how effectively a developer can engineer high-performance systems.